Alright, what's up everybody? My name is Joshua Bayham, and today I'm going to tell y'all about Lab 2 lines of charge. In the last lab, we looked at what would two pieces of tape look like and how much charge would they have if we treat them like 2 point charges. Um, but of course this is a very, very inaccurate oversimplification. Tape being, obviously relatively long and skinny, it's more like a rod than anything than a single point. And you can see what we treated it like in lab 1 in that picture. But what we want to treat it like is more like this picture here, where we have infinitesimally small point charges uniformly distributed throughout the tape, on each piece of tape. Um, and then we are able to look at the force of charge pushing up and the force of gravity pulling down, calculate these forces, and then find a more accurate model for what the stored charge on a piece of tape is. So, as I alluded to earlier, we can divide the tape up into n amount of sections, and each section would have a charge q, which would be equal to the total charge divided by that n. And as n approaches infinity, our data will become more and more accurate. And I'll touch upon that closer to the conclusion. And while our assumptions are a lot less than what we made in lab 1, we still are making a plethora of assumptions, such as ignoring air resistance, assuming each piece of tape has the same charge, and well, essentially is the same piece of tape, which is an inaccurate assumption. We're assuming the charges completely uniformly distribute, and we are assuming the tape is completely linear. We're treating it, as I alluded to earlier, as a rod rather than like a piece of tape. So our procedure for this, it's very similar to lab 1. What we're going to do is create two pieces of U tape, as you can see in that top diagram to your right. And we also, it is important, even though this is a different experiment, and even though we know that our U tape did have a negative charge from lab 1, we still want to make sure that these pieces of tape have a negative charge. And we'll do this by the same observation we did last time, by testing with a negatively charged rubbed pin. This is because if we have one piece of tape that's charged and one piece of tape that isn't charged, well, as we've been learning in physics as of late, that a neutral object will still be attracted by a charged object. So we want to make sure that both pieces of tape are negatively charged. We'll set them up in the diagram on the bottom right of your screen, right over here, and we'll determine the distance that the top tape raises. Well, this is the exact same as lab 1, right? So we can use our same data, it's just in this lab we are going to be solving for our data differently, if you will. So if you'll recall from lab 1, at least here are my measured data between the tape length, width, vertical distance, and the amount of charge, with it being a point charge. Okay, so what we can do is we can set up a Glowscript code to calculate the electric field um, treating these pieces of tape as rods. And remember, we've been learning these formulas for rods. So we have all the data to plug that in. We just need to set up a variety of code to do so. So upon setting up that code, and I don't feel the need to get too into the code, we're just taking it from basic code and manipulating it to ourselves. So I just took some screenshots of running my code here, and I'll leave the code in the description if you guys would like to look at it. So I have n being equal to 10, n equal to 100, and n equal to 1,000. And as I increase my value of n, we can see that the tape charge with a distributed charge decreases pretty significantly, at least from 10 to 1,000. And as this continues to increase, we will get closer and closer to a true value. And that true value would be about 6.01 times 10 to the negative 8th coulombs. See, now, computers aren't great for calculating or are great for calculating an interim, but they can't find infinity. So if we wanted to compute an exact value, we'd have to use an integral, which, I mean, you guys go to Georgia Tech, that's not the most mind-blowing thing in the world. So by using an integral, we'd be able to take every infinitesimally small piece of charge. So just to reflect, I found my single point charge to be 1.46 times 10 to the negative 8th coulombs of charge. And with the distributed line charge, it's 6.01 times 10 to the negative 8th coulombs. Well, that's a 412% increase. How is that possible? That's a pretty drastic increase. Well, our line charge is taking into account every single infinitesimally small charge, rather than just two oversimplified point charges. And this cuts out a lot of error in our calculations. And again, while we are still making assumptions, these assumptions are way, way, way less dramatic. We are using a much, much more accurate model using these rods. So that about sums it up. Thank you guys for watching, and see y'all guys for Lab 3.